So good morning again. So yesterday it was a bit heavy in the side of the speaking too much in details about how to build neural networks and how to tune parameters and these things. Today I will go. I'm going to touch a little bit more in practical details, how this is applied in practice, and how also I will show you some novelty that we are developing for Inspector and also as a contribution to the community, that is how to use deep learning also to do your leakage assessment, how to verify what your device is leaking and where it's leaking using deep learning. So I know I imagine that everybody here is quite familiar with sidechain analysis, so I will not explain this part initially, so I will go more directly into the application itself. So, but just to recap a little bit, we know that deep learning it's for that. So you have your target, you have your product that you're developing or evaluating, and you collect your traces, you create your neural network, and then what you can expect to get is keys from that, and also you obtain your metrics. However, if you start analyzing much better what your network is actually doing for your target is when it's processing the traces, you can see that inside the network there are a lot of activation paths for every specific class on the traces. So for a long time the community started to speak, so it was more like marketing or something more like to emphasize how cool deep learning is, but they are saying that we cannot explain what is inside the network. We cannot say how actually a big neural network is doing for my data. But actually there is a lot of answers for that, and there are a lot of methods that you can explain how a neural network treats your data in order to make the classification it does. And this can be done through the verification of the activation path, which I will explain here. So if you understand the activation paths for the traces, for what the neural network does in your traces, you can understand which part of the trace the network is actually learning from, and which samples are more important for the decisions the network is doing. So, and this is really important because if you are developing a target and you want to know how secure this target is, or if you are evaluating it, you can map all this activation, all these decisions in case of when deep learning is successful to implementation flows, vulnerability, source of leakage, so you can understand how good your countermeasures can be, or how, let's say, how the implementation can go wrong, and again sidechain analysis. So, and if you use this methodology to do your fixes and improvement on your target, you can also this helps in the faster certification, also in having more secure products. So it's a methodology that really can help in the development. So if we let's say from chess, I could realize that people is trying to speak about the future of sidechain analysis all the time, but basically sidechain analysis needs to comply with all these steps. We cannot skip any of them if you want to do a proper sidechain analysis. But let's say we have your product, you want to build your setup, you have to do, if you are doing EM analysis, you need to do your scanning, acquisition, optimization, a lot of alignment, leakage assessment, the attack itself, and also interpret the results. What people expect for the future is that all this part on the right side could be more automated in order to reduce the time we need to deploy sidechain analysis. This is, I think, it's a little bit too much for the future to automate everything. Of course, the setup construction cannot be automated because it's a manual procedure, but some of the steps can be more efficient if you use a machine or decisions to do it. My opinion is that this is a little bit far away from now. However, what we are working on now is we are trying to verify how at least we can make the second part there more efficient. The part where you combine analysis and the result interpretation. How you can optimize and speed up this part even more with tools using deep learning, for instance. So let's say that the deep learning plus sidechain analysis state-of-the-art is something like, we have frameworks today, not only for sidechain analysis, but a lot of frameworks are, let's say, really helpful in the sense of making deep learning practical and easy to work. And basically what we see people developing and proposing is supervised and unsupervised learning, of course, the two fields of machine learning. And we already know how to configure neural networks. This is more or less clear. And we are already answered the questions like it's better or worse than other methods. Is it worth to invest on this start? So it's proved that it can bypass countermeasures, misalignments. So it's strong enough to be used, to be considered. However, the one part that is still missing, and I think there will be a lot of discussion in the future about it, is how to explain the results that deep learning provides and how to use them to automate and to make better analysis. So I would say that today we have the framework, the basic framework is complete. We know how to define an initial neural network. We know how to make the training, to observe metrics, and we know what to do, to make it generalized, let's say for the validation, for testing, and we know how to combine the deep learning results into a key recovery, key enumeration part. So this is all done. But what is not done yet is the interpretability of the model, of the neural network. This part is still an open question. If we go back for the classic methods of sidechain analysis, like correlation analysis, for instance, of course, we know that the target's leaking if we see correlation peaks. So that's the distinguisher. This is what tells us how this method is good or bad. Template analysis, which is a supervised method, for instance, we use points of interest. If you don't see them, if you cannot identify them with some method, we say that, okay, the target is secure. We do, for instance, TVLA analysis, and we don't see the peaks, we don't see the indication of leakage, and then we just consider that, okay, one attack could not be worth to do because it's, if I don't see TVLA peaks, I don't see leakage. So it's my metric. But for deep learning, it's a bit different. You don't see the peaks like you see in TVLA or t-test, but you need to do some combination of how the traces, the input information is somehow related to how the neural network was trained. So how the network updates the internal connections, the weight. This is related to the input data, and this is how what we use to interpret a sidechain analysis using deep learning. This technique to understand what exactly a neural network sees from data, it's called visualization and in the community. And this is used for instance, for object detection in image. When you put your picture on Facebook and it knows that your face is here or there, this is what visualization is doing for you. It's just mapping the input data to the decision and showing where the information is located. If you are familiar with the frameworks for deep learning, you probably heard about Keras, which is one of the most used frameworks. So TensorFlow is from Google. It's a huge framework, and Keras is it was built over the TensorFlow in order to make it more simple. So it's a very good framework, and there is a book from the Keras creator that proposed different visualization methods, and 3 of them interpret the input information and how it is related to the layers in the neural network. So basically it analyzes how the intermediate activations are created when you provide input data. Also, when you use convolutional neural networks, because this is one of the main contributions of this author, it also analyzes how the filters are implemented, how the filters are contributing to the detection of the feature inside of the network, and also how to create some kind of heat maps for the activations for specific classes. So this book I really recommend. It's a really good book, and it's very easy to learn and to do the tutorials that it recommends, and really boosts the learning of deep learning if you consider it. So it's a really good one. But one of the methods that he proposes is how to understand, if you have an image, how to understand what the neural network is capturing from that image to make the decision. So for example, if we have a picture of elephants and you have a neural network that is trained to recognize elements in pictures, and the network is saying, okay, this picture is linked to the elephant because it's 99% elephant. And to understand which part of the picture actually the neural network is learning from, is using to make the decision, you start doing some occlusion on the input data, let's say removing pixels from that, until you reduce, so you kind of slide this some box over the image where you make the network to go wrong, to decide it wrong. And then when you find a place where it's decided, making decisions wrong, let's say now it says that something else is not, it's not the elephant anymore, then you know that that part is where the feature is located. So this is a very simple method to do the feature localization in images. So Facebook is also using this technique, and this is why it's very fast for them to identify what is a face, what is not a face. So, but for this technique has some limitations for sidechain analysis, because it needs a lot of manipulation of input data. And traces, it's like we don't have sometimes the leakage is located in only one sample or one part of the trace. Sometimes the method that we use combines different parts of the trace in order to make the decision and to break the target to recover the key. So if we use some technique like that, I would say that we have something like quadratic complexity, like we are similar when we do high order analysis. So we tested this technique inside, and we have a student doing this work, and he said that this technique is very limited to apply sidechain analysis. We cannot really identify what networks learns if you use this technique. And the reason is, I can illustrate here. So for instance, let's consider we have a convolutional neural network with many different layers, 2 convolution layers that creates a feature map, which provides you a connection to the dense layers and also the output. And I provide a trace, and this trace is, my network is saying, okay, this trace is a Hamming weight 5. And if I want to understand how the network decided that, if I would be able to see inside of the network, I would recognize an activation path. So the neurons that really read information from traces, the samples, and make the decision towards the output where it says, okay, this is Hamming weight 5. However, this method is not so easy to apply for sidechannel, as I explained in the previous slide. So we proposed a method that can start from the output layer and go layer by layer till it finds the input data. And by doing this, it's much more efficient and much more precise for identifying where exactly the neural network is learning from traces, why the network is deciding something based on the activation path. So going to more practical results, let's say we have this is just an example, it's a toy example, of course, it's not realistic, but let's say we have a software DES implementation, and this target here, if you apply deep learning, you get 100% of classification accuracy. It's very, very leaky. And if you take this a trace from this target and we apply something like t-test, like leakage assessment, you can see on the first key round, for instance, the first key byte, you can see a lot of leakage, a lot of peaks. And these peaks are quite significant. You just run any test on here and you recover the key. And this is the result from the visualization method that we applied. So you can see that the picture here, the colors are not really intense, but you can see that they are very aligned with the place where the TVLA is showing, the t-test is showing peaks. So where the network is learning from the traces is really the place where the leakage is located. It doesn't learn anything from where you have noise. So another interesting part is that, okay, if we take this range where when the network is saying to me, okay, I have leakage here and you have leakage there. So if we apply CPA on those parts, on these intervals, you can succeed. But if you look at the second figure again, you see some small peaks, some ghost peaks there. And if I select these small intervals to apply my CPA, it fails, meaning that what the visualization technique shows us as leakage is much more precise than what TVLA, for t-test is showing to me. So this ghost peak doesn't appear below because the network doesn't learn from that. And it's not learning from something that is not leakage. So this is just a proof of concept of the method, but it really emphasizes that if something appears in the visualization chart, it's because it's leakage. If it doesn't appear, it's because it's something else. So in practice, the approach that we use, it follows what we explained yesterday, but as I can show you in an example later, it's not very complicated. So you basically have to define an initial neural network. Of course, you train it, and then you apply the visualization technique to verify where the network is learning, and then you get something like that. So you probably get a lot of peaks and a lot of places where the network is saying, I'm learning from all these places. And then you say, okay, this is not good because I cannot identify more or less where is the interval where I should apply my attack. And this is a case where the network doesn't generalize very well, and then it's kind of overfitting. And if you optimize your neural network by looking to these results, I don't know, maybe applying some regularization technique or increasing the number of traces, and you train it again and then you verify again, you see in the visualization that now a lot of information is not anymore being captured from the neural network, because the second network is better than the first. And what we have here, so it's more localized information. And if we now focus the analysis on these peaks, on this part where we have more, where the network is telling me that it's learning from, we can optimize the attack interval, and then we go for the validation. So it succeeds. So this is more or less the framework that we are proposing, and then of course it still requires the definition and optimization of the neural network, but again, I will show an example where the configuration of the neural network sometimes doesn't need to be really precise, precisely defined, I think. And this example is based on a masked AES. This is a public database, DPA Contest, so I think all of you already know it. This is DPA Contest version 4, it's not version 4.2. Version 4.2 is more protected, but I will explain why I selected this one. So we have 40,000 traces in this database, and they were measured from a smart card running ATmega 163, and I think it's 8-bit microprocessor. And it is protected with rotating S-box masking. So, and this implementation was already very discussed in academia, and they are saying, okay, this is not really protected. There are some leakages around. If you use the information they release in the website, you can break this target with many methods. However, very few methods can break it as a black box attack. So, and then the attack we tried here is black box. We don't consider any information about how the masking everything is implemented. So there is a little bit of leakage in this target from proof of concept, which is not really strong, but for our case it's good enough. And in this case, the validation key and the training key are the same because they are collected from one single device. And I will also discuss later how we treat this part using the visualization, in order to avoid what we define here as false learning. So false learning, I mean when you think the network is performing well, but it actually is not. And for several configurations, a neural network can learn anything. So any key you provide there, it thinks it's correct, but it's not. So I will show you how to avoid this thing. So the masking in AES, in cryptographic process, is more or less like this. So you need to mask, let's add some masking to the input information, and then after the encryption or decryption process, you remove this masking. And the masking modification should happen for all the encryption or decryption process to provide the sufficient randomness to your target. So if you try to break masked implementations, you probably need some quadratic complexity, meaning that you need to brute force a lot of combination of samples, which is high order analysis. And in this target specifically, this is how this is constructed. They have fixed masks in the implementation. It's an array of 16 bytes. And for every trace, they implement a random offset of ranging from 0 to 15. And the masks, two different masks are selected from this array. So the first one is based on the offset index, and the second one, we call M0, it's coming from the offset +1 mod 16. So the MI and MO will be different, and they are used to mask the input value in the first S box. So yeah, so the input, the plain text is XORed with the first mask. And then there is the key addition,
the S-box normally implemented, and after the S-box, this is implemented all together actually. There is another XOR of the S-box output with another mask, and then you have the masked S-box output. So I took the information from the mask values and I implemented some leakage assessment on there, let's say considering white box scenario, where I have the traces here in the upper part, and I computed for all the traces what is the masked S-box output and what is the ID value of the masks. Also, I correlated that with the traces, and I see that, okay, for the range I'm interested, there are some peaks. So there can be some leakage. The Hamming weight of the masked value is leaking. So if I take as a black box scenario where I target the output of the S-box without any masking, I don't see any correlation. So meaning that the leakage is not really a first order in this case. And this is using some points of interest selection methods from Inspector. I ran this considering this leakage model that is XOR of S-box in, S-box out. And the only method that really showed me some small peak was the correlation, but it was not strong enough to recover with first order analysis. So the noise is quite high because the peak is not really higher than the rest. Sometimes it can be confusing. But if you target only this region, then you might get something, but it's not really converging for all the key bytes. And for the Hamming weight of S-box output, we can slightly see something here, but it's not really showing anything. So it's not really promising if you do a leakage assessment on this target, even if this is a software implementation. So this is some results that we achieved and also that we could see from the website. So we applied the correlation analysis on this target and we got average key ranking as 153. So it should be 1 to be successful. And we see that with 40,000 traces, first order analysis, a black box attack doesn't succeed. Also, template attack, we almost succeeded, but if we select very carefully the points of interest, knowing exactly where the S-box is processed, then we might get something close to the key recovery. The final ranking was 15. I think combined with some brute force method, it can succeed. The deep learning application on that, as the results come later, it was successful with only processing 10 traces. But also I could emphasize that other methods can work on this target. Let's say if you really spend time using second order attacks or collision correlation analysis, other machine learning methods, they can also be successful on this target. So I used 2 different neural networks configurations, and you can see here that they are not really different from the standard configuration. So a multiple layer perceptron was 3 hidden layers and 200 neurons each. And so some of the parameters I used, I didn't tune these parameters, I just selected that and then I applied. And also I implemented a convolutional neural network on that, with only 1 convolution layer. And this is the trace, the full trace of this implementation. And if you do some filtering here, you can recognize where the operation has been used. So add round key, S-boxes, shifty rows, mixed columns. And I was interested in this part with process the S-boxes. So applying directly the technique, the visualization technique, I trained the neural network, the multiple layer perceptron. And what this network told me, so the method told me that there are some places here in the trace where my network is learning information. So I applied my training on 4,000 samples, in a range of 4,000 samples, and I couldn't recover the key using this all this range. But my final key ranking for byte 0, for instance, was 11. So not so far from the key recovery, but it's still not successful. But if you take a look at the result of the visualization, the magnitude of 2 peaks are quite higher in the middle, telling that, okay, my neural network is learning that information from there. even if it's not successful. I'm not considering traces in the validation phase. This is what exactly the training traces. So I don't even need to know the key of the target for the target I'm trying to break to understand that. So I also did the same for CNN, for convolutional neural network. And coincidentally, I saw peaks on the same, so the visualization showed me peaks on the same places, similarly. And if you, some of the metrics that we got, this network, I would say it was not really good because it overfits the data. My validation accuracy is very low, slightly above the random value, that should be 0.11. And my key ranking, my final key ranking was 16, so still not successful. So the magnitude of the peak that you see here is how many times the sample was for, so if I have 1,000 traces, for instance, and I have 16 values there, so for 1,000 traces, 16 times, my network recognized that sample as leakage, this, for example. And so these are the results I got. So from the CNN, so my accuracy in the training for the training set was almost 100%, meaning that is overfitting. And you can see in this chart that the accuracy went to 100% quite quickly. But my validation accuracy, that I'm using recall here because it's Hamming weight, was quite low, slightly above the random value. And basically this is overfitting, it's not successful. But using the visualization technique and looking to the part where my network learned it from traces, I selected this range. And then I decided to repeat the attack on this range, on where the network told me that there is leakage. And after I did it, I increased quite a lot the performance of the network. So the same network without changing anything on that, I didn't overfit anymore. I hunted only for 100 epochs. And the generalization now is quite significant. So in something like 1 minute, I could more or less recover. So if I would wait more time here, I would probably increase much more the training recall, but maybe the validation would not increase so much, but it's good enough for my case. It's good enough to break this target. And remember, this is a black box attack on the masked AES. So after processing only 11 traces in the key recovery part, I could recover the key. When you do when you have obtained results from any framework in deep learning, what it tells is the confusion metrics, where it compares what is the predicted labels and what is the actual label. So here I'm using Hamming weight, and this is why you have columns ranging from 0 to 8 there and 0 to 8 here. So, and if you have a very high accuracy, a very good result, you should get some values like in the diagonal, showing that the predicted value and the actual value are quite the same. Interestingly, my confusion metrics in this target was like that. So, and this is still, I'm still trying to analyze why my neural network understood the leakage like that. So the value I expect, it's not the masked value. This is like I'm labeling my traces as like a white box, a black box attack. So I'm saying I'm not assuming there is any masking. But when I assume there is some mask, let's say my Hamming weight is even. It predicts as even, and when it's odd, it predicts as odd. So, and you can see here in the confusion metric this behavior. So somehow my neural network is mapping all the Hamming weights that I expect to be even to even Hamming weights, and Hamming weights that are odd to odd Hamming weights. So this is still, I'm trying still to understand what is going on, why the neural network is doing this, but it's recovering the key using this part. So probably my best guess so far is that the layers inside they are doing some kind of reversing part on the XOR in the S-box output. It's understanding that there is XOR there, and it's doing it automatically. Okay, so after succeeding on this target, I decided to do some analysis on how realistic is this attack, because I need to validate and train a target using the same key. And then I would say, okay, what happens if I change the key? Can my neural network still learn from traces and still break a target, thinking that the key that is recovering is the correct one, but it's just something random? So then I started to do this analysis. And one thing I recognize, and also I read from a paper explaining this topic, that is neural networks, they can learn from any random label. So if you take a trace set and you label this trace set at random, it will still overfit. So it can still associate something that you put as random to samples. And to avoid this thing, we need to understand how the neural network is learning from the data to see if this is happening or not. And why this is important? So for instance, if you're doing an evaluation on a target or testing your product, you can have some false verdicts about the countermeasures. You can easily say, okay, the target is protected, but it's not. But maybe it's not. So or I would say the target's broken, but maybe it's not, because it's just your evaluation is not correct, your assumption is not correct, and this can affect quite a lot of decisions, like the due rating or the level of security of a target. So, and using this technique, it also allows you to deploy deep learning on the same target without changing the key. So if you can keep the key the same for training and validation, then you can still go for this analysis. So it doesn't limit you to have different keys in different targets. However, this methodologies for evaluation is still not in practice, because we need to agree on methodology with the schemes for that, to apply that. So this is an example where I have the same key. This is still the DPA contest. And this is the results when I train my network with the correct key. And this is when I train my network with the wrong key. Of course, the accuracy here is not good, because I cannot recover a different key. So the key that I'm recovering there before, it's really the key from the target, because if I change my key candidate, it doesn't show any convergence. So this is just using the recall, I can also already see that the network doesn't validate something that is not the correct key candidate. But the most important is to visualize what the neural network learns from target. So if I modify the key of my device and start doing not modifying the key in the traces, of course, but just in the analysis, you can see that when the key is correct, the network learns only the leakage. It doesn't learn the noise. And then here, if the key is wrong, it still provides higher accuracy, but doesn't learn anything from the. It doesn't learn only the leakage, it learns everything. So it tries to adapt to the noise. So this shows how this observe what the neural network learns from targets, from data. How using the visualization technique, it's important for the evaluation. So this kind of complete the second part of where you only look for the metrics. Now we are also looking how the machine is also performing the job. Okay, so this closes this part, and just for you to, if you use Inspector or if you are waiting for new features, I would just to quickly emphasize here what we are implementing. So there will be, together with the deep learning module, we are still in the test phase, but we are planning to combine a local host application where you can observe everything that is going on during your training. So this helps a lot you to understand what's going on with your analysis. And also this visualization technique where you can observe what the neural network learns will also be integrated. So you can also observe more. You can also see what are inside the network, like layers activation, how every layer is separating the classes. So this also helps. Also how the weights are updated. So you can also understand how the backpropagation is doing the learning part to make some modifications on your target. Something new also will be that you can, you don't need to wait anymore till the end of the training. So if you have a very long training, a very long big data set, and you want to train for a long time, you don't need to do the full training before you start doing the test. So at every time you are doing the training, you can already proceed testing, and then you can already understand what is going on and to abort, to restart. And this is really important because the time here to train can be quite long, can be hours, so immediately you can already start doing the test and see how the key recovery is performing. And finally, this is something that we are almost finishing, that is, there will be a compatibility with every cipher in Inspector that is supported by Inspector, so if you implement the new cipher there, you can also use deep learning to that. So today the module only supports AES in this, and it will be integrated to all the ciphers in that is supported by Inspector. And the final part here is that we are finding a better performance when you are attacking bigger data sets. So we are using a similar structure that you use in big data analysis. So before, what we have is something like that. You have a trace set, and you need to process all the mini batches in this trace set until you reach one epoch. Okay, this can still be done, but there will be another option that will be if you have a trace set that is way, way bigger, and you don't need to process everything to finalize one epoch. The machine will process something, pick it up something from at random inside of the trace set, and continues training and training forever. So, because to process one entire epoch in a huge data set is quite it takes too much time, it's not really realistic. So this will be, you cannot use epochs as a metric anymore, but the iterations itself. So the advantage of this method is that it reduces overfitting quite significant and can easily be integrated with data augmentation. So that's my presentation. I just want to go back to the first slide where I was speaking about the future of sidechain analysis. And so, as I said, automatize everything is quite a dream, but today what we are doing is to combine the second part here, and then the combination of visualization with analysis, it's already in this direction. So we can use the visualization results, and if you can automate the interpretation, that it can optimize the analysis quite a lot. So that's it for today, and if you have questions, yeah, I'll be happy to answer that. Thank you.